Hello students, welcome to this module, which is part 2 in a series of modules on the basics of hydrodynamic stability, which is part of the course CG 614 of IIT Kanpur. If you remember, in the last module we tried to linearize the Navier-Stokes equations in the context of combined co-et Poiseuille flow, right? So there finally we ended up with a set of linear coupled partial differential equations that had Vx prime for the perturbations. Remember that we wrote the vector velocity v as the base state velocity v bar plus v prime, the perturbation. Okay, the perturbation velocity vector has vx prime, vy prime, vz prime. Also remember that the perturbation is a three-dimensional one. Perturbations are three-dimensional and time dependent in general. And of course you have the pressure, and you have these are the four unknowns, and you have four equations, partial differential equations: the continuity equation or the mass conservation equation, the x, y, and z momentum equations. So along with suitably prescribed boundary conditions plus initial condition, we can in principle solve this set of linear PDEs. Even if not possible to solve analytically, you can solve them numerically. So that's the whole idea. But the problem with solving this using that approach, which I'll call this prescription as the initial value problem, or the IVP in short. Okay, the problem with the solution of this even numerically is that the initial conditions are not known precisely in any fluid mechanical experiment involving laminar turbulent transition. Okay, so usually what you do is for a natural experiment wherein you are not deliberately perturbing the flow with a special class of initial or special class of disturbance at time t equal to 0. You just start the experiment and you find that the flow becomes unstable and undergoes a transition. So the initial conditions are, in most commonly done experiments, unknown. This means that we are faced with a very peculiar situation in hydrodynamic stability. The governing equations, the linearized governing equations, are known, but the initial conditions to which they are subject to is not prescribed. Basically it's unknown. Okay, now how do we get around this? How do we with this imprecise knowledge about initial condition, or with the lack of knowledge of initial condition, then how are we going to predict stability? Okay, this is a key question. Now I'm going to illustrate this, and the method that is used to get around this puzzle or problem is called the method of normal modes. I'm going to illustrate this in the context of a simple linear 2x2 system of ODEs. That is, I have dx dt is equal to ax subject to x at time t equal to 0 is equal to x0. Okay, this A is a matrix of constants, in that it is independent of the vector x is x1 and x2, both are functions of time, independent of x and time. So just some bunch of numbers. Okay, now how are we going to solve this? Okay, the standard way to solve, one of the standard ways to solve, is to say that first I will solve for the eigenvalue problem for A. That is, I will solve AVI is lambda I VI. Okay. Now for there are two eigenvalues if you are considering a 2D system. So let's say we solve for the eigenvalues and eigenvectors. Okay. Now then what we are going to do is that if you assume A to be a matrix such that you have two linearly independent eigenvectors, in this case because you're considering a two-dimensional system, in general A has, let's say, n linearly independent eigenvectors, then one can expand further. We can even further assume that they are not just linearly independent, they are orthogonal eigenvectors. Then we can expand x of t is I equals 1 to n ai of t v. Okay, this is the unknown solution for this problem, and I'm sorry, let's use a different I'll use ci because a is reserved for the matrix. These are the constants. Okay, instead of finding for instead of determining x of t, if I find the constant ci of t, then I have finished solving the problem, right? These are to be determined. Okay, now what you're going to do is you substitute this expansion to this expression, right? Dx, what is dx dt? Is summation I dci by dt times v. Okay, right? Now I'm going to substitute this back out here. This is nothing but summation a times x, sorry, a times x. Ax is, instead of x I'm going to write a ci of t av, but av is nothing but, sorry, avi. I have to be careful with the indices. This is I, this is I, but avi is nothing but lambda ivi, right? So I can use this to replace this as lambda ivi, right? So let's go to the next page. Okay, now because if vi's are orthogonal, then we can take inner product with respect to vj, and then you will find that dcj by dt is nothing but cj of t times lambda j, or cj of t is cj at time t equal to 0 e to the lambda j t, and therefore the solution x of t is nothing but summation I equals 1 to n cj at time t equal to 0 lambda jt. Okay, now how are you going to find these coefficients? We know that x at time t equal to 0, we have to use the initial condition here, this specific initial condition. So you will get, okay, so the cj's at time t equal to 0, okay, are basically the coefficients of expansions of the initial condition in the eigenvector basis. Sorry, I have to write vj, because remember there is vj here, so I have to write vj or vi here, because here everything is written in terms of j, so I have to use j. So the cj at time t equal to 0, because it is known, the initial condition, if it is known, if known, then we can find cj's by using this expansion. Okay, so this is the general solution. So if I have a linear system of coupled ordinary differential equations where the eigenvalue problem for the matrix A is, and we have assumed orthogonal eigenvectors, then what you found is that the solution is nothing but x of t summation Ci time t equal to 0, okay, times e to the lambda I t. Okay, this is the solution for this differential equation. How are you going to find Ci of time t equal to 0? It is nothing but x naught, the initial condition x naught, which is also known, is expanded in terms of Vi. Okay, so that's how one finds, because this is known, you can find Ci from this expression. All right, now imagine, so basically the details of the initial condition are comprised or contained in this set of constants. The specifics of the initial conditions are present in the constant, because remember that lambda I, Vi, the eigenvalues and eigenvectors are independent of initial conditions. They're just functions of the operator A lambda I is Vi lambda I. Okay. Now, so all the specifics of the initial conditions are here. So for a given initial condition, it's easy for you to find this, find the set of constants from this expansion of the initial condition in terms of the eigen vectors of the matrix, and then you substitute these coefficients here, the constants here, then you can find that solution at any time t. Now, if I tell you that we do not have precise knowledge of the initial condition, this is the case that is very close to what is encountered in hydrodynamic stability. Often we don't impose a special initial condition, we just let the flow be and then start increasing parameters like the velocity or the Reynolds number, whatever, right? Suppose you don't have the initial condition. What can we say about whether an initial condition will blow or grow exponentially in time? Yet can we say if IC will grow exponentially or decay exponentially? That's the question, right? Now the answer is very simple. Even if I do not know Ci, okay, suppose I erase this and say that's a common no, don't know. Okay, even if this is the case, you can still comment on whether any given initial condition, which is now characterized by the set of these constants, will blow or decay with time by looking at this. Okay, now if lambda I are real, then lambda is greater than 0 should be unstable, and lambda I less than 0 will be stable. Okay, so even though we don't know the the precise nature of the initial condition, you can still look at the exponentials and the eigenvalues which occur in the argument of the exponentials to conclude whether the flow is going to blow up exponentially in time or decay exponentially in time. So this method is called the method of normal modes. Instead, in fact, we don't do all this. We say that we'll take a typical sum from this typical term from this sum. Sorry. Okay. We say that let's take a typical term from this sum. Okay. And let's so what we do is we'll say that the solution x of t goes as some e to the lambda I t v I, and you substitute this back in the problem that we are interested in solving. Sorry, it should be is ax, right? Now I substitute this. So lambda vi e to the lambda it is a times vi is lambda I vi again. So vi lambda I e to the lambda it. Okay. So or we can do one step. So ax is e to the lambda it times a vi. Let's just keep it like that. So this gets cancelled right through, okay, leaving us with avi is lambda ivi. Okay. Now once you solve for the eigenvalues, then you can figure out whether the system is going to be unstable at large times, because we are only interested whether the system is decaying exponentially, which means if lambda i's are real, then they are negative, and or if it grows exponentially, which means lambda any one lambda I is positive, then the solution will grow exponentially. Okay, so in this system of ODEs where we do not initial condition is not prescribed, then we can see whether any initial condition will be stable or not by just looking at the eigenvalues of A have positive real part. Okay, so we have abandoned and altogether the idea of solving the initial value problem and using the summation to find the solution. Although if you have the luxury of knowing the initial condition, that would perhaps be the best thing to do. But in the absence of an initial knowledge of an initial condition, then the next best thing one can do is just to find the eigenvalues of the matrix A, of the operator linear operator A, and at time t equal to 0, if the perturbations decay exponentially with time, then it's a stable system. Okay, so in order for this to be happen, then all lambda i's must be negative. I'm assuming lambda is to be real, otherwise negative. Otherwise, if the lambda is are complex, then we should look at only the real part. Okay. Now, if it is unstable, then of course it will go exponentially in time. Okay. So, what the eigenvalue analysis will tell you is what is called asymptotic stability, or the stability as you take t going to infinity. Okay. Now, while this is a very very powerful approach, because it completely frees you off from thinking about initial conditions. So there are two strategies. You can solve the initial value problem if you have specific knowledge of initial condition, or you can solve the eigenvalue problem where you do not need the specific knowledge of the initial condition. But the eigenvalue analysis will predict only asymptotic stability. By asymptotic, I mean t going to infinity, large time stability. Okay. Now, this approach, while it is successful in many cases, it has one following drawback. When the eigenvalue analysis predicts that things are unstable, okay, I mean, I will use the word normal mode analysis. Okay, if it predicts an instability, then of course that means that the perturbations, even if one of the eigenvalues is positive as positive real part, then the perturbations will grow exponentially with time. It's unstable, and in order for you to consider the flow to be stable, all eigenvalues, real part should be less than 0. Okay, so then as time t goes to infinity, you will find that you are going to decay exponentially. Now, even if there is a exponential decay, so this is what we'll call stable. Even if there is an exponential decay at large times, okay, it is possible that at early times the non-normal, if the differential equation is not self-adjoint, then it will lead to mixing between the eigenfunctions when all the eigenfunctions are superposed. So it will lead to a transient growth or a temporary growth before decaying. Now this growth cannot be exponential, so this is called an algebraic growth, which means it will your perturbations may grow as t to the alpha, whereas alpha is 0.75 or something like that. Okay, so this is how one gets around the problem of taking into account the initial condition. Because we do not have a precise knowledge of the initial condition, we abandon all our hope of solving this problem for a specific initial condition. But yet you want to be able to say whether a fixed point is stable or not. Then what you have to do is to solve the eigenvalue problem, and if all the eigenvalues have negative real part, then the thing is asymptotically stable. But even if one eigenvalue has positive real part, then it's unstable. Now if the eigenfunctions are not orthogonal, then what will happen is that there will be generally a transient increase before it decreases. Okay, and this has nothing to do with the eigenvalues, because all the eigenvalues anyway have negative real part. So this occurs, this not transient or normal growth occurs because of superposition of eigenfunctions. Okay, because of superposition of eigenfunctions, even though all individual modes decay exponentially at time t goes to infinity, some modes which are not whose eigenvalues are not satisfied by okay I beg your pardon. So the point is, if all the eigenvalues have negative real part, then of course as time t goes to infinity, things will be stable. But that doesn't guarantee, especially if the system is not a self-adjoint system, that doesn't guarantee that you cannot have such a behavior where the disturbances grow and then eventually decay. That growth is called transient growth or non-normal growth or algebraic growth. Okay, so essentially what we are trying to say is that if you are interested only in asymptotic stability, then you can do away with the prescription of a precise initial condition and merely find the eigenvalues. And if all the eigenvalues have negative real part, or if they are simply real numbers, then if all the eigenvalues are negative, then stable. And even if one of the eigenvalues are positive, it's unstable. Okay, so I'll stop here for this module. In the next module, I'll motivate how we can understand Navier-Stokes equations, the linearized ones that we derived in the last module, how to think about the method of normal modes for such a case. Thank you.